Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Kiara Hansenne, who will be telling us about, I guess you changed the title to Fundamental Limitations of LOSR Quantum Networks. So Kiara is a postdoc in quantum information theory at CAA Paris-Saclay in France. Her research focuses on entanglement theory, quantum networks, and quantum tomography, with a current emphasis on quantum error correction. And she completed her PhD with Otfried Gune at University of Siegen in Germany, and has collaborated several times with experimentalists. So Kiara, the floor is yours.
Hi, yes, so thanks very much for the invitation to talk to in your seminar. Yes, so as you mentioned, I kind of changed the title a bit because the idea is that, so you invited me to talk about this paper that we had recently on arXiv about quantum networks, but it's quite a technical paper, and we had a previous one that was already in 2021 that has similar ideas. So I'm going to talk a little bit about that one too. And that's why the list of authors is also very long. So this would be here the collaborators from the first paper that we had on the topic. And then here are the collaborators for the one that was this year. Yes, and then as said, so it was for a collaboration between the University of Siegen and of Düsseldorf in Germany. And now I'm in Paris indeed. Okay, so the general topic of the talk would be about quantum networks. And I mean, nowadays it's quite agreed that quantum networks are needed for many applications of quantum computing, such as secure communications or distributed quantum computing. And there's also currently a lot of experimental efforts that is being done to realize like building blocks of these network structures, such as repeaters, but also entangling links over large distances and so on. But then, of course, if we want to have a functioning quantum network, we also need the network to be able to generate and distribute highly entangled states in order to make use of entanglement and be able to have applications that are working like QKD and so on. So in order to have that, people model quantum networks in very different ways. So sometimes they consider that there's only bipartite links, so you can only distribute something like Bell pairs, or you could have some nodes that have a higher number of parties where you could distribute GHZ states and so on. And most importantly, some models of networks would be using classical communications and some would not. So these are the decisions that we have to take in the beginning when we define what we mean by quantum networks. And what we did in these works is to consider LOSR quantum networks. So LOSR stands for local operations and shared randomness. So the idea is that if we have something like a quantum network, so we have different parties that are connected. We mostly looked at bipartite quantum sources. So this would be in this setting that we have here. So here would be the easiest example where we just have a triangle. So we have three parties. And what we do is we send bipartite quantum sources between every two pair of nodes like this. And also then they can apply local operations. So something like this, they could each on their node apply some kind of quantum channel. And everything might also be correlated and organized by pre-shared classical correlation. So this would be the shared randomness. And then we end up with something that looks like this, where we have basically a network here of three parties, where we have quantum links here. The gray one would be only classical distribution of randomness here. And this would be the local operations that they can apply on their nodes and might be correlated by, coordinated by this variable lambda here. So this is what we end up with the definition here for what we will call our network state. So the triangle state here in the case of the triangle network, where we have our sources states that are distributed, we have our local operations, and then the shared randomness that we have here. And then the question that we asked was, well, are these LOSR networks useful? So can we use them for some quantum applications? And in more details, what we looked is, can they generate highly entangled states? So this would be the question that we started with. If we have a model of a quantum network like this, can we generate a highly entangled state in such a setting? So with basically no classical communication, so that's the important part, because then we cannot do protocols such as teleportations and so on. So you cannot just teleport a quantum state to share it within the nodes because there's no access to classical communication in our model. Okay, so now that the definitions are set, I'm going to first briefly explain what we had in these results from the 2021, so which basically were constraints on network states that could or could not be produced in these networks. I'm going to briefly explain the idea because it's much more intuitive than what we did later, so I think it's still interesting. Okay, so for this, we start with the 4-qubit cluster state. So that's a, well, as it says, 4-qubit quantum state that is highly entangled, and it's a graph state. So for people who don't really know what graph state or stabilizer states are, the idea is that this state can be defined as being the unique common +1 eigenstate of 4 operators here that we call generators. So this would be here tensor products of Pauli operators. And all of these generators here commute, so it's possible to find a common eigenbasis, and then we just take the +1 common eigenstate, which is then defined as this cluster state. And then we ask the question, well, the same question, can it be generated in a square network? So now we move to square networks. So the example I had before was a triangle, but here would be something like a square, but it's exactly the same idea, right? So we wonder, well, can we create such a state in such a setting here, which is very different from having something like might also be called a network or not, depending on their definitions, where we have a central node here that would generate the state and then distribute it to the 4 parties. So what we showed is that actually no, so this state cannot be generated in such a setting. So here, of course, if we just generate the state and send it to the parties, we can do it no problem. But here we will show later that it's actually not possible to create such a state. And then we wonder how close we can get, and for this we want to have bounds on fidelities. Okay, so the general method to do that is that we use what is called the inflation technique. So that was developed in these 3 papers here for, it started for classical causal model. So it's a technique that basically wants to see if a behavior fits or not a causal structure. Oops, sorry. So I'm going to briefly explain what it is. It's quite technical, but I'm still going to make sure that everyone can follow. And the method that we use is we find a statement that is true in some kind of inflated network, which I'm going to explain later. Then we bring it down to the original network, and then we obtain constraints on network states. Okay, so I'm going to break this down. And the idea is that, as I said, we use this inflation technique, and the basic principle is that if some kind of state can be created in a network, so let's say we have a state rho here, and we can generate it in such a network, it means that there exist sources and channels in order to build it, right? So you can find sources here that you distribute, you can find local operations on A, B, and C, and then you can build your state rho. So that's the basic assumption. But then if you can do that, you can also just copy or use different copies of your sources states and your channels to build other types of networks. So other states can be built using several copies of those sources and channels. So for instance, we have the state tau here and the state xi. They use the same sources, so the colors would be the same sources. On the node, you apply the same channels, but it's different states, right? Because this one, for instance, would have 8 qubits, whereas this one only had 4. And then we can also do something a bit more complicated where we rewire a bit more complicated things, but the idea is the same. You just use the same sources and the same channels to build a new state, what we will then call an inflated state. Okay, and then what follows from that is that some marginals of these 3 states, so rho, tau, and xi, must be equal. So how can we see this is, for instance, if we look here at the state tau, but we only look at what happens on B, C, and D. So we trace out everything and we look at the reduced state on B, C, D. So this state here, tau on B, C, D, if it is not equal to your original network state here on B, C, D, then what you can deduce is that your original state couldn't be generated in the square network. So the idea is that if you use this inflation technique and then you obtain a state tau based on your original state rho, and that you end up seeing a contradiction so that the marginals are not equal, then you conclude that your original state could actually not be prepared in the network. So this is the idea that we're going to use, is that if it was possible to create the state in the network, then these states tau and xi must exist. And if they exist, their marginals must be equal. So if you end up with a statement that says, well, the marginals are not equal, then you had a contradictions and your original state couldn't be prepared. All right. So now, how did we use this to obtain constraints on the network states? Well, the key observation is actually that some of the stabilizer elements, so this is related to our graph state that we had at the beginning, but it's not very important. It's basically just Pauli operators. They anti-commute in some kind of inflation. So here, if we look at these three operators here, so x on b prime 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 and x on d, so this would be the blue here. Then we have the purple and the orange. They anti-commute in this setting because they only overlap on the qubit labeled with a D. And if they only overlap on this qubit D, since Pauli matrices anti-commute, they all anti-commute. And what is known in general from quantum states is that if you have operators that pairwise anti-commute, such as these ones here, then the sum of the square of the expectation value is upper bounded by 1. So this is a statement that is always true if you have operators that anti-commute. And that's what we're going to use. Because now if we know from the inflation technique that these expectation values here, they have to be equal to your state rho from your original square network. So your inflation technique tells you that if you can generate rho in a square network, then this expectation value must be equal to that one of your state xi in this inflated network setting. So since these must all be equal, we end up with a relation here that holds for square network states. So for states that can be generated in square networks, the sum of the square of the expectation values of these three operators must always be upper bounded by 1. But these three operators, they commute. Now in the smaller setting, so only in the square networks, they actually commute. So this is a non-trivial bound on general states. So now if we go back to our cluster state that I introduced at the beginning, which is then, I repeat, the common eigenstate of these four operators, we can see that this is then just the inequality we obtained on the previous slide, and I just rewrote it here. Well, these are products of these generators. And since our state is a +1 eigenstate of these operators here, if we now inject our 4-qubit cluster state in this relationship here, what we end up is that if you can generate it in this square network, then you obtain a contradiction because you obtain something like 3 is smaller than 1. So using this, we basically say, okay, if you assume that you can prepare it in your square network, then you arrive at the contradiction because of this inequality that we showed here. So we basically conclude that we cannot generate this 4-qubit cluster state in our setting of network with local operation and shared randomness. Then we had a bunch of these inequalities, so we can do it for different types of operators, and then they can also be used to bound the fidelity of network states. So this would be the observation that we had in this first paper that I mentioned, where we showed that no state with a fidelity to the 4-qubit cluster state that we define like this, higher than 0.74, can be generated in the square network. So this now was just a very brief introduction into what we did in the original paper. So it was just to set the stage a bit about this inflation technique that we used. Then using it, we obtain constraints on network states. So for a state to be able to be generated in such a LOSR network setting, then they must respect a list of these constraints, and then we can also bound the fidelity of what we can obtain. Okay, so I'm just going to briefly mention the results that we had in this first paper. Yes.
Sorry, can I just ask? I'm just curious, like the number 0.74, is it easy to understand why this number?
Yes, so it's an analytical construction, right? So here I just wrote it in how much it is, but the idea is that if you have such inequalities, right? So you constrain how much the expectation values of these observables can be. So I don't know how familiar you are with graph states.
have some familiarity.
Okay,
Yeah.
because what actually for graph states, if you want to estimate the fidelity of another state row to this to any graph state, right? In particular, this one, you just have to sum the expectation values of all the stabilizer elements. So here I've only listed a few, right? Because you have much more of these stabilizer elements for the graph states. But if you sum them, you obtain this fidelity. And then now what we did is to maximize the sum of all these elements under the constraints of these inequalities here. And then what comes out is this number. So because these basically are constraints on the correlators of your state row, and they then restrict the expectation
like
value.
how compatible you can be.
Yes, exactly. Yeah.
All right. Okay. Thank you.
Yes. So yeah, I didn't explain in so much details because I wanted to have time to.
Oh yeah, sure. Yeah,
work,
I wasn't even sure if I should have asked, but
no worries.
Yes,
feel free to ask at any time. Okay. So now I just wanted to mention briefly what we had as a result. So I showed you something about the 4-qubit cluster state because it was a bit easier to understand because the others are a bit more technical. But we basically did the same with GHZ state, and then we also had a bound on the fidelity saying that if the fidelity is higher than 0.7, well, 1 over square root of 2, then it cannot be generated in our triangle network. This is the ones that I showed you. So basically this fidelity bound for our cluster state. But then we also showed that graph states in general up to 12 vertices, or graph states whose minimal degree is not more than 3, and all the 2 and 3 dimensional cluster states cannot be generated in multiple partite networks. So actually, then we also had a small result about symmetric state, but the thing here is that it was really case-by-case results. So here, why did we stop at 12 vertices? Is that because actually graph states up to 12 vertices are listed in some database somewhere, so we checked them one by one, and they turned out to all violate our constraints, right? But then it was very much case by case. We looked at it, and we kind of, in the end, needed something a bit more systematic because we didn't have really very general claims. It was more like, case by case. So yes, that would be for the first part. So maybe if someone else has a question, now would be a good time.
So, yes, I have a question.
Yes.
Maybe I should first say hello. So, hello, Kiara. I'm also a PhD. I was a PhD student of Dagmar Booth. So, I spent a lot of time in Düsseldorf and Siegen. Yeah. So, by the way, my question is about here you have a threshold for a state that can be generated with this LOSR.
Yes.
Does it mean that if I have some state fidelity weakness, if I can locally measure the state fidelity, then actually I can detect the classical communication?
Yes. So that's the idea. So if indeed you have something that is larger than that, then it means that one of the assumptions wasn't it wasn't held. So basically, mostly it would be classical communication, but it might also just be that your source states have higher time. So if I go back to this one here, so it could just be that, okay, you don't have classical communication, but you have one central node that sends everywhere.
Okay.
But yes, in
I
a sense,
see.
it can be used as a witness to detect that the model that you have is not enough. So that's what you can conclude.
I see. Okay, actually, yeah, it is not we cannot simply exclude one of the, let's say, we cannot simply exclude classical communication, but there may be some other. Yeah, I see. Okay. Thank you
But
very much.
I mean, in a way, like if you are sure that you only have bipartite sources because you trust network setting, for instance, then yes, then you could say, okay, there was classical communication involved.
Okay, interesting. Thank you.
Okay, then I will move on to the next part, which is then so the paper that you actually contacted me to present on the fundamental limitation of quantum networks. And for this, what we're going to do is that our starting point will be here the GLZ state. So in the paper, what we do is that we show that the largest fidelity to a GLZ state in such a triangle network that you can have is lower bounded by this number and upper bounded by that one. So what you can see is that there's still a separation, right? So we didn't completely fill the gap. But yes, compared to, for instance, here, the previously known gaps, we reduced it a bit. So this was what was known before. So we already knew that the largest fidelity achievable by a network state to the GLZ state was actually higher than 0.5. But then we closed a bit this gap. And what's interesting here is that actually, as soon as you have a fidelity to the GLZ state that is higher than 0.5, it means that you have some multipartite entanglement. So from this, which is a bit surprising at first, it follows that it is actually possible to generate a multipartite entanglement state in this setting, right? But as we can see from the upper bound, they cannot be very entangled because it's still not very high, right? This maximal fidelity that you can achieve. So here I'm gonna briefly present how we obtain these lower and upper bounds, but it's quite technical, so I'm just gonna give the general idea, but I won't go much into details because then it gets a bit complicated, and that's why I wanted to present the first part because this one is a bit more accessible. Yes, and then what we did is that using these bounds, we extended it and we showed that for any graph state now, so not only the ones up to 12 qubits, how we presented before, but for any graph state, the fidelity achievable by LOSR network states cannot exceed the one from the GLZ state, so that one. Yes, so that's going to be the program for the next slide. So first, in order to get the lower bound that I presented on this fidelity to the GLZ state, what we did is to explicitly construct states in the network setting. So what we did is we constructed local channels, and then we used sources states like this, and then we optimized them in order to maximize the fidelity. So if I go back to my previous slide here, we still have this triangle setting, right, where we send sources states here between the nodes, and then we apply local operations on the nodes on A, B, and C. And here, how we basically constructed these local channels. So first, we just try to numerically optimize the fidelity to the GLZ state by doing seesaw methods so basically what we did is to optimize over channels and then optimize over sources and then optimize over channel and so on, back and forth. And then one of our co-authors analyzed a bit more in detail how the channels looked. So from this numerical optimization, how did the channels look? And here would be some kind of very sketchy representation of the Choi matrices of these channels. So that's why I'm saying it becomes to be very technical, right? I just showed it here to have something on the slide, but it gets quite technical. So here all the details are in the appendices of the paper. But what is interesting to know is that basically from these results of these numerical optimizations, we were able to construct channels so local operations that we could then manipulate later. And we still then use these ones that looked quite regular to optimize over the sources state. So this would be the sources state that we send between the two parties. And what we did is we did that for different local dimensions. So we started with qubits here, where we just then send, so again, I go back here, we would send then 1 qubit there and 1 qubit here. And then we went higher. So it would be then we send one Q treat there and then a Q treat there, then a Q quote and so on. So we increase the local dimension of our source states that we have here. And then, yes, so what we noticed is that if you increase here the local dimension, so for your source states that you have here, then by doing this optimization over the source state, we can see that the largest fidelity that we can achieve also grows. So it grows and it kind of seems to settle to a some kind of limit value here. And what's interesting to learn from this optimization technique is that the source states that came out to maximize the fidelity were not maximally entangled states. So it wasn't here that we would, for instance, send bell pairs between the parties, right? It was something that was a bit weaker entangled than bell pairs. So that was also an interesting observation. Yes, and then finally we thought, okay, maybe since this maximum fidelity seems to increase with the local dimension, maybe this could also be turned into some kind of dimension witness, so that we would say, okay, if we are above some fidelity with a GZ state, we can certify that the local dimension of the sources are at least, I don't know, like 4 or something like this. Okay, so this was a very brief sketch of how this explicit state generation was done. And then we use these explicit states basically to compute the fidelity. So we know that the largest fidelity that we can obtain is at least this. So that would be the idea.
I just wanted to ask, so why did you stop at 10?
Because then it became computationally complicated to optimize.
Okay. Like it runs very long and...
Yes. And also, I mean, as you can see, it kind of settles towards some number. So we were already relatively satisfied with this. Okay, so this would be then for the explicit states and the lower bound, right? And then here would be then for the upper bound. So then here we have an analytic and necessary criteria for states to be able to be prepared in such a network, but it's also long and technical. So here I'm also just I'm flashing a few formulas, right? But it was a few pages of computation and then it was also quite technical, but the very brief idea is that we start from the fidelity to a GZ state from any state, right? That can be then expressed with this, that is upper bounded by this expression here, which involves correlators. So the Pauli operates on A, B, C, and so on. So we started from an expression like this, which is true for any state. And then we basically used, again, this inflation technique that I presented and also results from other papers on the same topic, which would also be then these LOSR networks. And then in the end, what we obtained is that the maximal fidelity achievable by these LOSR network states to the GZ state, can be expressed as a optimization problem again. So, and then if we solve this optimization problem, we have the bound that I showed before. So yes, this is also just a very quick slide just to say that it is long and technical, but that would be basically the general idea. And that's also why I presented earlier before the results of this other paper, where then you could get some kind of intuition of how we can use this inflation technique to have bounds on fidelities to other states. Okay, so now I go back to this other slide. So basically what I now showed you very quickly in these two previous slides is that we found a lower and an upper bound on the maximum fidelity achievable by these LOSR states to the GZ state. Yes, by explicit state construction and also derivation of analytical criteria. Yes, and then what is left for me to show is what we want now to show is that the largest fidelity achievable by any graph state is then the same upper bound, but then this GZ upper bound. So this is what I'm gonna now show in my remaining time. Okay, so now we go to networks of arbitrary size. So we are not in the triangle setting anymore. We have a network which could have as many parties as you want, but that is basically every party is connected by a bipartite link. Okay, And now the basic idea would be that we assume that we can prepare a graph state that we call G in our n-partite network, so in our big network. And then what we're going to do is we're going to group the nodes, right, of our big network. We group the nodes to form a triangle. So this A, B, C here would have many parties that we group into being A, and then B, and then C. And then what we now want to do is we want to apply a big unitary on these many parties here, a big one on these parties B, and then finally on the C one. So we want to apply big unitaries on our graph state that we assume that we could prepare in the network in order to split it in a GZ state and some kind of rest state tau that doesn't matter much. Okay. So first, what we did is that we proved that this is actually possible for all graph states. So for all graph states, it's possible to find unitaries A, B, and C to, in the end, do something like a GHZ state extraction, right? So we want local unitaries on 3 groups of nodes to produce at least one GHZ state and some remaining state that we don't care too much about. Okay, so we showed that for every graph state, it's possible to do that. But then from this, we can directly see that actually this leads to a problem, because then if you would be able to prepare your graph state in your big network, then you just reassemble the nodes and apply your unitaries and end up with a GHZ state. But before, in the previous section, we already showed that it is not possible to generate GHZ state in such a triangle network. So we already arrive at a contradiction, and from this, we can already exclude all the graph states from higher arbitrary size networks. But then not only excluding all graph states, we wanted also to have a fidelity on, we also wanted to have an idea of how close we can get to these graph states. And for this, we have to notice that if a network state, so if a state that can be prepared in a network has some fidelity F with the graph state G, so something like this, then it's possible to create a state in the triangle network that has at least the same fidelity F with the GHZ state in the triangle network. So this would be then how we use this fidelity bound, right? So because again, we arrive at a contradiction, because if we have a state rho n that has a fidelity F that is higher than the bound that we had earlier with the state G, then you could prepare a state in the triangle network that has a higher fidelity than the bound that I showed you previously. So we again arrive at a contradiction. So this would then be how we can conclude that no graph state can be prepared in these local operation shared randomness networks with bipartite sources if they have a fidelity larger than the GHZ bound. Okay, so that would be now the idea of how we use the bound for the GHZ state in order to have an upper bound on every graph state. And just as a side note, actually here I showed you for the GHZ state and the n-graph states, but this this idea also works for any other state that you would put here, and any other state that you would put instead of the GHZ state, if you can show that you can, with local unitaries, go from one to the other, which we did for all graph states, but if you show it for some specific state, it also holds. So this is a bit more general than what I presented. Okay, and then we get already to the end, so to the results of this second part, which is then, yes, so this is the first one that I mentioned. So in the triangle network, the fidelity with the GHZ state of our LOSR network states is between these quantities. Then we extended it for qubits. So now we are still in the triangle setting, but instead of having qubits in your edges of your triangle, it's any dimension, right? So we extended this formula also. This is the one that I presented, so that no graph state can be prepared in these LOSR networks with bipartite sources if they have a fidelity larger than that. Yes, and then what was also interesting to remark is that now if we have networks that have at least 4 nodes, or at least the square or higher, we showed that now the fidelity to the GHZ state must be smaller than 1 over d. And interestingly, this is actually the bound of separability. So it means that below, you don't have genuine multipartite entanglement. And then this fidelity is also achievable by separable states. So if you have more than 4 nodes, or at least 4 nodes, then this LOSR setting is really not so useful because you cannot even generate multipartite entanglement. Okay, then I showed you before already these cluster states, right? So we also extended the bounds for more general cluster states, but maybe that's also not so interesting to go into the details, but just to mention that we also did something in that direction. But then the big conclusion of our paper would then be that these local operation and shared randomness networks cannot faithfully create large multipartite entangled states. And therefore, as a setting in order to create multipartite entanglement for quantum information applications isn't very useful. So we would, in the end, need classical communication or long-lived quantum memories in order to achieve something interesting with this network. So the conclusion of our paper would be mostly something in the sense of, in the direction of not using these local operation and shared randomness networks for quantum information tasks. But still, it was quite interesting. I mean, it's, as an academical problem, it's still interesting to know what can be done with these networks. Okay, then this is then already the end of my talk. I would like to thank you for the attention and also for the invitation again. And this would be then my collaborators from Siegen and Düsseldorf.
All right. Thank you very much for a very informative and insightful talk. Yeah, okay. I think we actually sort of like lots of time for questions. So if anyone has questions, please feel free to unmute yourself and ask it now.
So may I have a question?
Yes, sure.
Thank you for this talk. So now this network setting have a constraint on bipartite entanglement sharing scenario. If you want to extend this to, for example, tripartite state sharing, is the technique also the same, or you need more advanced mathematics?
No, then you would need indeed some more advanced techniques. So especially for the fidelity estimation. So let me see. Yes, so if I go back to the results of the first paper that we had on the topic, right? For the case of the symmetric states, right? So we also looked a bit more in details about permutationally symmetric states. Here we actually, this proof actually works for no matter the size of your source state. So if you have a network with n parties, if your sources distribute states to at most n-1 parties, because of course you don't want one central node to distribute to everyone. But as soon as you have at least one that is not involved in the sources, then you cannot generate these permutationally symmetric states. So for instance, a GHZ state or any state of that type. But there we were not able to have fidelity bounds. So this we could exclude the states, but then not have these fidelity bounds, because then, yeah, it would be a bit more complicated, I think, the proof techniques.
Okay. Yeah, I can see that it's very challenging. Thank you.
Is it possible to describe like in what sense does the proof technique depend on the bipartiteness of the sources? Maybe not so easy to describe.
Yes, I need to remember now. So partly it's because the results that we used here are also for bipartite networks, right? So this wouldn't, this would already need to be replaced. But then in our specific proof, I don't remember much if and where it happens, except in these results that we used.
Yeah, so actually maybe I don't know if it's a follow-up to this. So you can, like, maybe I can do like sort of small extension where now let me allow just two parties to communicate,
Yes.
but not so. But I don't know if, like, if you've looked at this and how much better can you get the fidelity.
So
this
we already thought about the question a little bit in the sense of exactly like as a follow-up work, right? Because then it would be interesting also to know what is the minimal amount of communication you would need in order to do a GZ state and so on. But this did not really go beyond blackboard discussion, so we don't really have the results in that direction. But it's definitely a question that would be nice to address in a bit more details, yeah. Because the obvious thing you can just do is, teleportation, right? Then you can just have like bell pairs between everyone, and then you just you produce your big state in some kind of factory node, and then you can just teleport it to all your different parties. But if you can do better than this or not, this I don't know.
Yeah. Right. So let me see if there are other people who wants to ask questions, or maybe some comments. Okay. Yeah, maybe I just like one question from me. So when you like, you did mention that because of this, there is actually possible to generate like a multipartite entanglement.
Yes.
Quite a noisy one, but still.
Yes.
But is like, do I know sort of like can I quantify how good it is? Like, do I have an idea of what the state that I get actually looks like?
Yeah, so this would be then if we use our explicit construction, right? So in the appendices of the paper, we write then the example of the state that we get using this technique. So really, like the density matrix is written down. And yeah, so for us, a figure of merit that we used is then, since we optimized it to be highly close to the GZ state, right? This is then what we used, and we ended up with having this fidelity that is slightly above 0.5, right? But it's not great, as you mentioned, it's quite noisy. So that's what we used as a figure of merit in order to see how good these states could be and if they would be actually useful for something. But then there's works of other people where they mostly then consider networks where they then only send bell pairs between the nodes, right? So they have a big network, and then they analyze how many bell pairs do you need to connect everyone, and to have something interesting, and to have a genuine multipartite entanglement between the nodes. And there also, like, if you just send here bell pairs between your nodes, so you already have GME, so you already have genuine multipartite entanglement. But the thing is that then you end up here with 2 qubits per node. So you don't have a 3 qubit state, but you have a 3 quartz state, right? And yeah, then the situation is slightly different. But yeah, but then you directly get something that is GME if you just send bell pairs and do nothing else.
I see. Okay.
So maybe I have another follow-up question or discussion. So far, the scenario is like the sheer randomness is sheer among all the parties.
Yes.
Yeah. And then my question is that if we have some kind of different hubs of this sheer randomness in a network.
So if we have different what? Sorry, I didn't get it.
Different hubs.
Yes.
Yeah. So So we have some sub nodes, they share randomness, with another set of sub nodes, they can share randomness, but not all of names can share randomness together.
Yes.
Is this scenario can be a special case of this result, or you can simply extend this result to this scenario? So,
yeah, so
I think like for yeah, please, sorry.
So the thing is that actually there's so about this shared randomness, the idea is that if you don't have it, then the set of states that you can create in these networks, it's not a convex set. So then that's, well, there's two reasons of why we would consider shared randomness. The first one is why not? Because it doesn't weaken our model. So we just included it, right? Because there's no reason not to. And also because if you consider it like more like practical construction of these quantum networks, well, shared randomness is very cheap. So we just included it. But it also makes then the set of states convex. And I think that if you have different hubs of this shared randomness, maybe it's good if I put again the definition that we had here. So if we have the definition of the state, so that's what I just said, right? If you don't have this shared randomness, then if you look at the set of states that you can prepare, it's not convex. And then I think if you have these hubs, you would end up in the same situation that you would also end up in a non-convex set of states. And then, for instance, the fidelity estimation, you could still do it the same because that one does not depend on the shared randomness. So the upper bound with the fidelity estimation would still be the same. But then, yes, the construction of the states too in the end, because they also don't need the shared randomness. But I think making then general claims about these networks would be slightly more complicated since you don't have this convexity.
Yeah. And when it is not convex, is also troublesome. Yeah.
Yes.
Thank you.
Right. I think, yeah, we have time maybe for one more question, if there's any more questions. If not, I will ask one final question.
Yes.
I'm just curious, like, because like there's a gap, right, between this lower and upper bounds. So I guess like the looseness comes from the upper bound, probably.
Yes.
What I imagine. Yeah.
That's what we're thinking. Yes.
Yeah. So, like, what do you think needs to be done in order to sort of close this gap?
So that's it's not so easy, right? Because what we have in the end for the proof of the upper bound is that we use what we do in the end is really that we have a bunch of these inequalities, right? That kind of constrain the set of states that you can do. And yeah, I guess for improving it, you would need more of these inequalities, but they are not so easy to derive. So that's so here I've shown you very quickly how we could derive some kind of constraints on this network state, right? And then in the proof of our last paper, we used results also from other people where they also used this inflation technique in clever ways in order to obtain these inequalities here. But yeah, so I don't know if the limitation comes from this inflation technique because everyone is using that in the end to have results. And if we would need to go to higher and higher order of this inflation, right? Because yeah, I inflated 3 times my network, but I could go higher. And then would going higher give me some better constraints? But then it gets, again, very complicated because you have more and more parties. So that's
like is it not known? Like, I mean, maybe it's complicated, but can you foresee that obviously if you go higher order, you'll get a tighter bound? Or this is not obvious?
This is also not obvious. So this inflation technique, it's also like a numerical hierarchy that you can implement, and yes, then it is proven to converge in some setting, right? That if you have some extra assumptions and so on, you can show that this hierarchy converges. So in the end, you wouldn't, in principle, be able to have constraints that would fully characterize your set of states. But I don't know if analytically that would be a big challenge.
Yeah. I see.